We can also go through the weekend thinking about MATLAB and what it can offer you. So let's talk about what we're going to talk about. Okay, what we're going to talk about is this: a couple toolboxes in MATLAB. One of them is the filter design toolbox. Okay, which is also related to the signal processing toolbox. In fact, they both, when you look at the GUIs that drive them, the graphical user interfaces that drive these things, both of them actually call on the same thing. Okay. Another one, Wavelets toolbox. So these are all add-ons. So right now, maybe you have, you know, the basic Honda Accord is your MATLAB box. Now you trick it out with an air conditioner, super sweet tires, spinners, okay, stereo system, okay, all extras. So the nice thing, though, is you can get them. Student versions are like $29, $39 each. Hopefully most of your department. So in other words, it's not astronomical to get these add-ons if your department doesn't have these things, or even if you have the student version and you want to just get the add-ons to these to kind of ramp up, put steroids on your MATLAB, this is it. And 29 bucks. I think you usually, you know, if you're doing steroids, probably more than that per month. And this is like one-time fee. All right. What are the advantages to these things? The advantages, forget it. Okay. Anyway, I'm on film over here. It doesn't matter over there. Okay. The advantages, pros. The pros of this, professional grade. As you will see, this stuff's pretty amazing, actually. So I kind of lied today. I said to someone, man, I don't know half the functions of these toolboxes. I kind of know a little bit about them, but I don't know half. And that was such a lie, because I probably know only 20%, not half. You'll see why. There's a lot of things you can do with this, but it's professional grade. If you're into digital filter, signal design, processing stuff, this stuff will do everything for you. It's really nice, right? You can build stuff with this, okay? In fact, by the way, MATLAB is a professional tool. Anybody own a Prius? Anybody? You could probably all. Has everybody ridden in a Prius? No? Maybe. But on the Prius, there's the little screen that you can touch, and you can monitor your engine. It looks at what your engine's doing, fuel economy, has all these graphics and statistics. You know what's running all that? MATLAB. That's underneath all that. It's super sweet, right, MATLAB? Now you're feeling powerful, right? This is what you can do with MATLAB. You can build a Prius, okay? So it's professional grade stuff. It's partly why they charge extra. So this is the basic package. You add on stuff like this. That's the big pro. If you want to do stuff, yes, you could write it yourself. But what you have here is people who are professionals writing it. And for the most part, if your application works, use it. They have current developments. This stuff is great. They have all these boxes to do stuff for you. Okay. Cons. Really just comes down to that. There's only one con. The con is it costs you money. I mean, right? Or if your department has it, who cares? You can use this stuff anytime you want. In applied math, of course, we have it, because that's how we roll, right? Yeah? Because we have awesome toolboxes in applied math. Some of the other departments might not be so gifted as far as MATLAB goes. But we're awesome. We got money. We're rollers. And if you want student edition, it's actually not that much. It's 30 bucks. So it's not bad. But that's actually the biggest reason people might stray away from it. You're paying something like this. Maybe you don't even have specific usage in mind to use it. So you might not want to be paying that because you don't have something in mind. But there you go. Stuff's there. And in fact, what I would say about toolboxes in MATLAB in general, aside from a couple of them, they are very heavily used. Like the PDU toolbox, by the way, partial differential equation toolbox? Never used. It's terrible. Okay, I'm not going to say it's terrible. It was really great, but it's the same toolbox that they had about 10 years ago. There's this company called COMSOL. COMSOL used to be FemLab. They were the ones, there was a group at MATLAB that built the PDE toolbox and said, hey, we're going to spin off to be our own company. And they had the PDE toolbox built, and that was about probably a dozen years ago. And then they just kind of kept it and left it there. Same thing with the symbolic computing toolbox. The symbolic computing toolbox in MATLAB is Maple version like 4. It's now in version 12. Okay, so 7 versions ago, 8 versions ago, MATLAB and Maple decided to make a partnership to say, hey, this could be really awesome. We can bring MATLAB power, Maple power together. And they did, and they couldn't get along. So they had a breakup. It was nasty, divorce. But MATLAB got to keep the symbolic toolbox, which was Maple 4. And so that hasn't changed in about more than a decade, too. However, those are bad boxes, but these are good boxes. Okay, so know the history of your box, and you'll know if it's good. No bad, nasty breakups here. All right. Everybody good with that? So now what I'm going to do is do a little walkthrough for some of this stuff in the toolboxes. As I said, I'm going to go ahead and start off with the statement that there's a lot of the features that I don't even know. These are very sophisticated tools, so if you are not into the signal design processing, there's a lot of functionality there that you would be unaware of. It would also reflect partly the fact that I have not touched on a lot in signal processing. You know, we've hit the big concepts, and you can take those big concepts and you can run with them and get very detailed. Okay? But this might be the kind of stuff that's very relevant to your work, depending upon what your research is. Okay? So that's what we're going to start with. And let's pull this down. Good enough. Okay. All right. So, yeah, there we are. There is our MATLAB. And toolboxes are accessed usually with some command. Sometimes it's kind of funny to try to find the command is actually a little bit difficult. But once you know it, it's easy. Okay? So the way you're going to do the digital filter design or the filter design toolbox is FDA tool. Filter design and analysis toolbox. So FDA, not Food and Drug Administration. You can't put food into your disk drive and see if it, you know, like swine flu free. Okay. If it could, MATLAB would be selling off the shelves. Last spring they would have had record sales. Everybody would be trying to put it in their CD drives. All right, FDA tool. And first of all, you get this Did You Know button. And I don't know, so I'll just close it. And this is your little platform. Okay. So let's talk about this little platform here. By the way, there's whole pages on the MathWorks page that talks about the use of this thing. Okay. So the way they break this up is the top is essentially giving you all the information currently about your filter. Okay. So there it is. Structure, direct form, FIR, it's a 50th order field. You see already the terminology that they're thinking about is different. But we'll get to some of the stuff that we've covered in a moment. Here's the magnitude in dB of your type of filter that you're looking at. We'll get to that in a moment. Okay, so it's fairly complicated. Response types of the filter. Here's where these are the buttons you get to play with, all down here. This is filter design, right down here. Okay, and the whole concept is you bring in a signal. So this does two things for you. You can either design signals and waveforms out of this thing, or you can process signals and waveforms out of these things to do very specific things. So for instance, you can come in here and file and import signals. Okay? And, oops. From these signals that you import, the idea is you can see what the properties of filtering are. But right now, this filter is just a concept where you can say, I want a filter that's going to filter out some bandwidth of a signal. It's going to have some extinction ratio between the center to the sides. How much do you extinguish in the center versus the sides? You have full control of this thing. You have all kinds of different filters you can apply. That's the kind of thing you do out of here. And then you can export the whole thing. So once you design a filter that you like, you can export it out to MATLAB and then use it for doing processing your signals. Okay? So let's do a few, let's look at a few things here. It's going to be annoying if this keeps happening. All right. What I need is on the iPhone, and I could just touch my iPhone and do it. That'd be awesome. Okay. All right, so let's look at a few things here. So here's the response type. This is a low-pass filter. See this region here in this box? So a low-pass filter allows through low frequencies. That's it. We can go to a high-pass filter. Check it out. A high-pass filter kills off low frequencies, and it filters over here. Okay? And you get to pick the width, the height, everything about that filter, and its location. We're going to come down to it over here, right? So here, I mean, this is the stuff. The f-pass, f-stop, it's determining all these parameters of the filter, where this stuff sits. And you get to control it all. You get to put it in units of hertz or whatever else you would have for this thing, okay? So there's a high-pass filter. There's a band-pass filter. There's the band you want to pass through. Band-stop filter. You want to stop a band from going through, right? So a band pass is say let one band through. A band stop is take a set of filters or a set of frequencies and kill them, right? Denoise in some sense. Maybe you have a signature. So for instance, by the way, a lot of people who do very sensitive experiments in physics, they take their data and they always see a 60 hertz component in it. It's due to all the electric current going at 60 hertz. There's a signature there. If you have very sensitive equipment, well, you might say, I want to get that out of there, right? So you just put a band, a band stop filter at 60 hertz, remove it from your data. Now what you have left is supposedly, you might have removed a little bit of the true signal too, but the idea is to say, let's get rid of the wall current signal that's actually showing up in my data, okay? So these are the kind of things you can do. Low pass, high pass, band stop, all in the filter design. Differentiator. Don't know. That's okay for me to admit, right? You'll still think okay of me? Yeah? All right. Well, I can only hope. Okay, let's go back to a low-pass filter. And I can decide what kind of filter I want it to be. There's a Butterworth filter, for instance. I can make a Chebyshev type 1 filter, Chebyshev type 2 filter. And we're going to look at actually the properties of this filter in a moment. So let's go back to the Butterworth. And within the context of looking at this thing, let me get this thing here, because there's actually some bottom buttons that, well, okay, we can't see them, big deal. So as you change things, it just changes the design of the filter. And let's go back to here. You can change everything you want. Where all this stuff happens, if the f-pass, let's make it 8,000. Sign filter. Okay, so the property is put in. So now what we're going to do, here's the magnitude response. And by the way, you can now start looking at all these buttons up here. These buttons up here correspond to what drags down on the analysis button. So let's take a look at what's on the analysis. When I hit the analysis button, I can look at different properties of this filter. There's a generic picture that here's a filter, what frequencies you want to do. But when I actually take a specific filter like a Butterworth, it actually has a very specific shape in the frequency domain, and there it is. This is actually the amplitude response. I can look at the phase response, magnitude and phase. All this information is available to you. So how you design a filter is you say, okay, here's what I want to do. I want to make a filter that affects the phase this way, but has minimal effect on amplitude, and somehow, you get to design this thing for whatever application you have in mind. That's the whole point of the filter, Typically, you're coming to this filter design toolbox saying, you know what I need? I need a filter that does this to signals. Takes this out, flattens that, cuts off this. Okay, go design it. Right? You specify what you want, and this thing gives you all this type of responses coming out of the filter. Okay, so you have all this degree of freedom and control. So if you are in signal processing applications, this is your tool. You can just come into here and just boom, 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 knock stuff out. Okay, it's all graphics-driven, menu-driven, very nice. Often used, for instance, optical communications. If you want to filter out optical signals and fiber optics, kind of clean them up, denoise, pass through different wavelengths that you need, this thing does it all for you. Okay. All right, so that's the magnitude response. We can look at the phase response of that filter. There it is. We can look at magnitude and phase, both together in the same plot. All of it's always in dBs. Okay. By the way, remember, this is a what kind of filter did I make? Butterworth. Yeah, it's a Butterworth. Okay, and I put the f-pass at 8,000. Okay, so 8,000 is the f-pass. So you see, kind of have this peak here, around 8,000 kilohertz, or direct. So log of 0 or log of 1, right? On a log plot, log of 1 is 0, right? So where it's 0 is sort of this important point. Okay, that's where the filter is height 1 in some sense. So that's kind of what you're looking at in something like this. And it's all on log plot. That's a standard thing to do in signal processing. What other kind of filters? And so, okay, analysis. You can go back here. You can look at group delay response. We haven't put anything in actually. This is a typical thing, unless you're looking at frequency chirped signals. This will actually have then an impact on that. Phase delay. See, we haven't built the filter to do anything on this. Okay, so let's look at like a high-pass filter. Actually, I need to actually do some other things to actually get a phase delay. Then we can actually look at impulse responses to the filter. Okay, so this gives you the response to an impulse, so you can start thinking about designing the filter based upon impulse responses and so forth. So anyway, I don't want to go into too much detail here. The idea is mostly I want to illustrate to you the fact that this tool exists. And if you want to get heavily into filtering and filter design and cleanup by using filtering, this tool is a remarkable thing to be using. Okay? And they have a lot of online tutorials that will go through and tell you how to do all these different, how setting all these different things will have different properties for your signal. By the way, you can also use this directly in MATLAB code. Okay? So you do not have to do all of this from a GUI. So the GUI is nice in the sense that you could say, design the filter, export it. But, and by the way, when you export it, now you can actually use it in MATLAB code. Suppose this filter is just one piece of your code. In other words, your code is, I've built some signal, I've transmitted, I've propagated on something, I have some equations of motion, now I want to filter it, and then do another piece of something else. So the filter itself is only one small piece of your code. And only here can you learn this command I'm going to give you next. It's awesome. I learned it recently. I was just so much impressed. I have to share. See? They're shouting about it already in the halls. All right. So in MATLAB, you can actually call directly to the filter design and analysis toolbox directly from MATLAB. Okay? And when you do that, you can actually call directly all these functions that we're talking about here. All this pushing buttons can all be directly called in from code. Okay? So here is the coolest one ever. It basically returns to you. You give it essentially nth degree filter that passes through with a normalized cutoff of omega n, so you get to specify some just basic filter properties, and what it produces for you is the actual filter design that comes out in these NPK, which then you can use in post-process. Okay, but I haven't told you the cool command yet. You ready? See, the lights came on for it. I'm going to put a Butterworth filter in there. Butter. Awesome. Did you know that? MATLAB has the butter command. Awesome. Full fat too. This isn't like, you know, unsalted, low fat. This is full fat butter. Awesome. Okay, so you maybe want in your lifetime to build a MATLAB code with butter in it. And people go, whoa, what's that command? Butter. Okay. I thought that's just the only thing I really needed to share with you about that, because I was so impressed by it that I was like, wow, butter. Okay, point taken? Good. Now we're going to move on to the Wavelet toolbox. So today's lecture actually, well, they'll both be kind of not too long. Well, I'll finish within time. But obviously, I've skipped over a lot of this toolbox. Obviously, I don't know a lot of this toolbox. But hopefully, what's obvious as well, 3 obviouses in a row, there's a ton of stuff you can do. And that's the most important thing I want you to take home from this, is that if you have applications, it is not that hard to say, oh, actually, I'm going to do a lot of filtering processes. This thing is just there, and you just import your data, boom, 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 boom. It's like, you could write your own code to do this. That would be dumb. This is easy, and it's done, and there's probably no mistakes in it, I'm pretty sure. Right? I mean, the one thing you should understand about code, right? The more code you write, the longer the code gets, your chances of writing a bug into your code get up higher and higher and higher. Okay? And if there's already a toolbox there, it saves you the time of not only writing the code, but also just it has all the bells and whistles for processing at a very high level. So you use these kind of things. Okay, so that is the filter design toolbox. The signal processing toolbox is very closely related, because what you do with the signal processing is you say, I got a signal. I want to process it. Typically, you process it with filters. So you take this stuff, the signal processing toolbox is kind of an add-on to this that just calls on this thing to do this to my signal, including, for instance, denoise it. Okay? All right. There you go. Now, let's move away from the filter design and analysis toolbox, which is right here. No. And now we're going to go to Wavelets toolbox. Now, when you push Wave menu, here's your menu. I would like the crab, please, with a little toast, and finish it off with tiramisu. If that was all on here, we'd all be like using it all the time. But fortunately, we can order up a 1D wavelet or a Wavelet Packet. They're not that tasty. But still, here's the menu. You know, soups, salads, everything. All right, so what are we going to do? Mostly what we're going to do right now is look over here, one-dimensional. What we've been talking about wavelets is decomposing signals into time-frequency signatures and doing wavelet transforms. Now, I've made the statement that wavelets come in all kinds of flavors. You can have the Har wavelet, which is very easy to look at. You have the Mexican hat wavelet. You have what's called the Dobashese wavelet. There are a lot of wavelets to choose from. Some of them look amazingly crazy. Now, you can write a code to construct all these things, or you could just, boom, pop it in here. All of it's there. All of it's at your fingertips. Okay? So that's what we're going to do. And what is the Wavelet toolbox often used for? The Wavelet toolbox is for a couple really big applications. One, image processing. You pop in an image, and what you want to do with an image, the power of multi-resolution analysis is that multi-resolution analysis takes an image, starts coding it at different levels of resolution. Takes an image, and what this allows you to do is do image compression. Wavelets now are the standard for doing wavelets are the standard for image compression. It used to be Fourier transforms. They used to do image compressions. Wavelets drops you way further down, and I think it's the standard in JPEG now. Okay, so JPEGs save all this space, and there's a reason for it. Basically, it's a multi-resolution issue. Take the picture out one by one to a given resolution level. For some of you who've converted into JPEG, right, there's this option sometimes, what quality do you want? Have you seen this? Quality is all about how many levels of resolution do you want? That's really what that question is asking, in a way. So once you understand wavelets, you understand that quality means level of resolution. That's interpretation. Okay, so image processing, denoising of images, all these kind of things. We'll actually look at a bunch of stuff like this. All right. So let's start off with Wavelet Packet 1D. I'll order that off the menu. Yes, I'd like a side of Wavelet Packet 1D. And you order it up, and then boom, this pops up here. And we're going to go here. So there's nothing there until I go File. Let's look at some examples. Okay. So what does it do for you? Well, first of all, here's your signal. It gives you an example signal. It gives you actually the coefficients associated with the wavelet basis that you use here. So remember, the one big thing that you have to do is when you expand in a wavelet basis, you have to compute these coefficients, which are inner products of the function you have projected onto the wavelet basis. Okay? And this actually gives you essentially, this is kind of that little box I drew, the cartoon of how to understand time frequency, and this gives you the decomposition tree associated with here. There's 3 levels represented here. And by the way, you can't quite see it here, but over here, let me pull this down. You see that, right? This is using a Dobashi's wavelet. You can also do this using a Haar wavelet. Then you analyze. A little bit different, not too much different. You can also use Koifman wavelet, level 3. See, a little bit different, but not too much. Let's get a better example. That one sucks. Sorry, can't say that. Let's do a continuous wavelet. This one's a little bit better. File, example. Yeah, that one at least looks cool. Okay, here we go. Here's an analyzed signal. What this is, you see this CAB? This is B, I think. No. A and B. Can't remember which one's which. But it's telling you all the coefficients of the wavelet expansion. Gives you the coefficients of the wavelet expansion for this signal. And here, what this is, here, right now, what I have is a total of 61, 2, 3, something like that. And what it does is it takes a slice right along the middle, and it plots the coefficients, and it plots basically, if I take that slice, what is the CAB look like along that slice? And this is this thing here. Okay? So go up here, slice it halfway through. That's what the coefficient strength looks like at that level. Remember, these are different levels of resolution. Right? So when you start off, you take the big scales, take smaller scales. This is what this time frequency picture was. This gives you the strength of the coefficients. And this here gives you the local maxima lines. In other words, you have a local maxima here, 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 and here. Okay, of this data. So it's process it all in a wavelet basis. And it gives you so if, in other words, you want to take a signal and you want to represent it in a wavelet basis, you just basically go File, Import, put it right there, say Go, boom, pops it all out. You got all the coefficients, export. Okay, you're done. It did the wavelet transform for you, basically. You have all the coefficients. So that's a nice process. So you can decompose any signal you have to a wavelet basis very easy with this toolbox. Just like the command window that you have for the signal processing, there's a nice command, CWT, that you can call directly from a command line window, provided you loaded the wavelet toolbox. CDW means continuous wave transform, pops out all the coefficients. So in other words, if you want to just pop them out and then go use them for something else, that'll do it for you. But this here is basically graphically represented on that plot. That's not all you can do with it. All right, Moss, are you ready? You're okay. I don't know about anybody else, but Moss is super ready to look at wavelets here. So this is one. By the way, you can set different wavelets to this as well, just like before. You can set different wavelets. It doesn't come up with good resolution here. I'm going to show you one other one here, which is, here's another one, Wavelet 1D. This one here is kind of nice because it actually, so all these different toolboxes do kind of the same thing, but they try to represent the data in a different examples. Here's a noisy signal with, sure, that one. All right. So here's same kind of stuff, but again, what this one is actually demonstrating for you the breakdown of the signal at different resolution levels. Here's your signal. Okay, it's got some periodic structure. It's actually got a lot of noise on it. Here's what the wavelet decomposition does. Takes out this. That's the big piece. That's the big scale stuff. Do you see any small scale in there? No. That's right, because the wavelet's supposed to not see that, right? You just take out the big scale stuff. All the small scale stuff comes at the next order. So you take out the big scale stuff. Now you go, remember the wavelet scaling function scales by an octave. In other words, by a factor of 2 in the frequency. That's the whole purpose of the scaling function. Scale it. Now you're getting something that's, what are all the frequencies that twice that fit into that category? Here they are. Notice one thing. You've basically, in this thing here, you've taken out this oscillation. So now what would be left is flat. Taking that out, now you got this. Now go one scale down this, one scale down that, one scale down this, this. Keep going if you want. Just keeps breaking it down. If this is kind of white noise process, then you can get very, very fine resolution, very fine fluctuations, and you can keep scaling it down and capture everything. But even here, it's interesting. Notice there's sort of a periodicity to the whole thing. I don't know if they put white noise on it for the signal or not. I don't know what's actually that composed, what was in that signal. But here's the thing. The decomposition at level 5, S, which is the signal, is A5 plus D5, D4, D3, D2, D1. So you add these up, boom, pop that out. Okay? So that's the idea of the wavelets. Pull out the big stuff, smaller, smaller, smaller. You can cut this off at any point you want. Okay. Now let me show you some other cool things about this one. And I can take this thing, and let me do one other example. I don't know. Let's do mishmash, something like that. I want to look cooler. No, that's not that cool. Anybody think that's cool? Nobody? Okay, we're going to do another one. Not that I expect you guys ever to answer, but sometimes I do. No? All right, let's just do this. Noisy bumps, fine. Okay, there's noisy bumps. There's a signal. Here's its decomposition to level 5. Over here, some nice processing pieces of information. This is your toggle. So your job is to load a signal. That's it. Boom, pull a signal, pops this out for you. Now you can start doing things. Okay? So this here, decomposition to a wavelet basis, and you can start saying, okay, I want to, first of all, level. It's a 5 level. Why don't we go to just 3 levels? Analyze. Okay? So actually, did you see a difference there? Let me see, go to 5. Yeah, so there's kind of a nice difference there. Let's go to level 3. Okay? There's level 3. And I can use different wavelets. Right now, it's using so this is a Dobashi's wavelet. The Dobashi's wavelet is kind of the coolest one. And by the way, Dobashi's 1, let's use that. The Dobashi's wavelet 1 kind of looks a lot like HAR. A little bit, discontinuous little things. Okay? And the Dobashi wavelets, by the way, are one of the most practical because they are one of the ones that have some of the best localization properties because they have compact support. And they have some of the best frequency localization as well. So Dobashi wavelets are kind of like the standard. Like that's probably one of the best ones to use. But the Dobashi wavelets look kind of crazy. This one doesn't. Kind of looks like HAR. But let me show you Dobashi's 2, which is used often. put it to 2. Oh, it doesn't do it so well. Let's go 3. Yeah. This is a bad signal to look at on. Okay. I can zoom in. I know you can do this. All right. Okay. Forget I can't do zoom in. Oh, did I do 3? Okay. Analyze. Okay. So the Debussy wavelets. Let me bring another example up here to try to get you. Sorry. There. Let's just do this one here. Debussy's to analyze. Yeah, okay, so these are kind of more like what the Debussy wavelets look like. They're very irregular in some sense. And you would say, wow, you're constructing all your solutions out of these funny shaped things. But these things are all orthogonal. They're compact support. They have beautiful properties when you mathematically, in an analysis point of view. But they're kind of funny-looking beasts. Okay, so this is very different, by the way, than Fourier expansion. The Fourier expansion basis, sines and cosines. We know exactly what they mean. Debussy wavelets are kind of these things. Like, wow. So the levels here, you start with this as the first level of trying to get that. Second level, third level, fourth level. And you get it all the way down to the fifth level. And that's a decomposition of that signal. Now, you can look at some other things about this signal. You can look at statistics. You can compress it, histogram, denoise. So let's go ahead and go to some of these functionalities. Denoise pops up another window. I'm going to have to shrink this down. Ah, shoot, doesn't fit, does it? So that's, okay. Well, all right, so let's, I can't quite, well, let's see. No. All right, so, all right, well, we're kind of in a jam here because the screen size is not matching up with my screen size. But here's the signal. Here's the original coefficients. And essentially what you can do is there's some unscaled white noise. And by changing the threshold values here, you can basically choose how you want to denoise an image or denoise a signal through this thing here. So for instance, you start setting your filter levels over there at what level you want to start cutting things off. Okay? So the lines show up here, and then you ask, okay, so how does this then denoise that original signal, and how do I sort of systematically take away the noise by doing this wavelet decomposition? So essentially, a lot like what we did in class for denoising a signal, we said, let's filter around some spot. This says, first project it into the Debussy's wavelets. Then, from the Debussy levels that we have, you denoise at each level of resolution. Okay? It's very different than Fourier, which it just says, just denoise the whole thing at once with one kind of filter. This denoises level by level. Okay? So people like this. It actually turns out to be quite a nice way to do it. What else can we do? Let's see if any of these other things, statistics, see how much of it fits on here. Here we go. Here's a histogram of that signal. Can I move this around? Associated with that signal, and you can't, it gives you the mean variance of all as you go along and as the cumulative. You can calculate all these things about minimum, maximum, medians, ranges. They're all down here. I don't know if you can read that, but there they are. Mean, median, maximum, standard deviation, L1 norm, L2 norm, max of the norm. So we can get a lot of statistics out of a signal. And this may be important for some application that you have in mind. You can compress the image, if you could see it. Sorry, this is usually, it always, when I'm on my machine, you can see the whole thing. I guess the one problem with the GUI is, right, it's not, it has a certain resolution that it's not scaling on the projector too. But this also basically is going to give you compression ability. Take your signal, compress it. Take a song. So what does MP3 do? When we burn CDs off a song, it used to be what? Is it MWave file? I mean, the typical format on a CD is high quality. It is. I mean, it's a WAV file. But a lot of MP3 players are, well, they're not a lot of them are. If they're an MP3 file, they're MP3 files. And the point is you want to take your whole CD collection and put it onto this little machine, right? Well, what you do is you compress the images, or you compress the songs, right? You decompose the song, and then you say, okay, what can I kind of throw away and still keep pretty good quality? All done with wavelets. The best compression techniques right now, I'm getting choked up, are all wavelets, okay? So this will allow you to do this. You don't have to just do music, right? I mean, we have these music files, but the point is you can take any data you want, and suppose you have really large data sets. Compression is all about saving key aspects of your data and figuring out what you can throw out, essentially. So this allows you to do that as well. Okay, so it gives you the multi-resolution levels. It compresses, denoises, all these things. Now, what we're going to show about this wavelet stuff later, so you can see how kind of sophisticated this is. This is all menu-driven. The only part you need to really do is import file, import signal. Boom. You are, like, in seconds, you have analysis of this signal computationally that's just like, boom, flying at you. You got more information here than you probably ever need. But for the specific application you might want to be looking for, you go figure out which button's the one you need to make the kind of analysis you need. And it's all menu-driven, very nice to use, state of the art. All right. So let's do that. Let's go back to our menu. That was a tasty appetizer. It's time for the main course. Are we ready for the main course? I am. Super sweet. No, it's actually, we want salty right now. Sweets for dessert. So salty. Let's go get some salt. I think I'll take the, where's my 2D? Yeah. I think I'll take the Wavelet 2D. This is the, and how would you like that? Oh, I'd like that rare, please. Thank you. So we have 2D Wavelet rare. File, load. Indexed images. This is one you see a lot in the help pages. Okay, so this is an example of what we just talked about, image compression. Okay, I talked about image compression as being one of the main uses of wavelets, and here's a specific example. You take an original image, has some high quality, let's say. It's not perfect. There are some graininess there. But what you do is you take the discrete wavelet transform on this, so you're going to project it off the wavelet basis, and what it's going to do is it's going to take that image, and it's going to sequentially take out the big scale features. What are the big scale features? Round head, background. There's a big patch here, patch there, round head. I mean, these are the big scale features. Then go to the next level of features. Then the next level, and then the next level. You can see there's a lot of fine scale structure here. But the nice thing about the wavelets just go, look, I don't need you to tell me where the fine scales are. I'll go find them. I know where they are. I'll go find these things, and I have a good signature of fine scale at this wavelength, sitting in 2D all around here. I'm just going to put that on one level of resolution, right? So this woman may actually have just one level of resolution up here, very strong signature, one down here, one down here. And this does it all for you. Here's the decomposition of the at level 2 is what it's called. Okay? And this is basically extracting out the level 1, the level 0 picture, level 1 picture, and then the level 2. Okay? So by level 2, you're already getting a lot of picking up a lot of the background noise. And then you've basically now compressed the image because you've only saved 2 levels of resolution. Look at the image with just 2 levels of resolution. There it is. Pretty good reconstruction. And you've saved a lot of space. So it's effectively like an image compression process we just went through. Okay? By the way, if we could see all the buttons we have available, oh, there we go. There's some. We could analyze it with different wavelets. This was done with a HAR. We can do a Dobashi's. Do a second order, analyze. There's doing a Dobashi wavelet reduction. Level 2, let's go to level 4. There's level 4. You see that? Now you're kind of, you know, it's 4 levels of revolution. Viva. Okay, boom, boom, boom. You get it all out. And the more levels, the basically should be the finer, the more true to the original image you have. Okay? All this can be done here. You can look at the statistics of the image. You can compress it, denoise it, look at the histograms. All this stuff is just right there. By the way, one of the sexy things about this, or wavelets, it's very easy to understand your data here. You have the original picture. You know what the ultimate comparison is to, right? You have high fidelity picture, and when you do, so one of the things that's really nice about teaching with, so next week we're just going to do image analysis, or we're going to talk about methods for denoising images, all these kind of things. And one of the things that turns out to be really nice about image analysis is it's very visual for you to see. I did better by doing this or this or this. Okay? But keep in mind, this could be, for instance, the temperature data over the North Pacific, right? And you want to say, look, I got all this temperature data, lots of fluctuations, and what I want to do with this temperature data is take out the big structure, take out the local variations. Can I gain some insight into that? By saving my levels, I can project down. Look, there's stuff happening on thousands of kilometers, but I have a lot of signature of stuff happening on hundreds of kilometers, right? By looking at it by different levels. Notice, we often look at images, but really this could be just any scientific data you have to begin with in 2D. And you just process that. And by looking at the levels, that's what you're looking for ultimately in any of your data. Characteristic signatures that are sitting there that you don't see just by looking at this. Okay? That's the kind of thing that you want to do with this. All right, so one more thing we'll do. Do we have one? I want to do a denoising. Wavelet Packets 2D. Let's see, is this one that does denoising? All right, file. Tartan. No. Okay, so this also does the decomposition of images as well. There's so much to play with. Here we go. Here, denoising. 2D denoising. Let's pull in one here. All right, we'll do, this is the last image and we'll finish here. So let's go to the noisy woman. Oh, you're hurting my ears. Okay, there's the noisy woman. She's not even moving her lips and she's noisy. And, but here's the image, thrown with some noise on it, and you want to clean it up. Well, typically it's going to be a lot like our filtering process we did before, which is you're going to say, let's put it in a wavelet basis, and for every level of resolution, let's try to put some filters on those level of resolutions, clean up every level, and then reconstruct the image. There's the reconstruction. So what you've done here is you've sort of smoothed things out. Right? You went from here, a lot of graininess, you pull this out here. I would say most people would probably think that's nicer, probably, right? I mean, sometimes when you clean up an image, it's not so clear, but here at least it's smoothing out over everything. Okay? And it gives you all the information of how this was done. Look at these. These are your little filters. You get to control them over here. Where you want to filter. What do you want to cut off at every single level? This gives you all the power and control you could conceive of for doing an image processing or a data processing. You have all the statistics at every single level. You can do this, look at residual, look at denoising, all this stuff here. You can do it in different wavelet bases. So this right now is in the wavelet basis, the HAR. You can ask, okay, how would the denoising happen if I used a Denoise wavelet basis, let's say of order 2, decomposed image. Come on. All right. Here's the thing. We've just proven that this noisy woman is a vampire. One thing about noisy women is if you put them in a Denoise 2 wavelet, they'll disappear. And it's the same properties as not reflecting in a mirror right there. I have no idea why that didn't work. You can quote me on that. Let's go to level 4, see if we get anything. No? It's not giving us anything. Okay, fine. Let's go to this one. Is the HAR the only one? Why is that the only one that's going to give me something? That's what I had before, right? Anyway, I broke it. Sorry. I'll pay for it. Don't worry. All right. Okay, so let's finish with this to final concluding remarks. We have the lights back on, I think. So here's the deal. This is kind of a weird lecture, right? I didn't like go and talk lecture. I hardly know the packages that well. The point, hopefully, the take-home message of all this is what you have available to you is very high-end tools. The learning curve, very small to get in. Mostly what you need is data. Whether you're going to do signal processing, image analysis, wavelet analysis, your startup cost is almost zero. If you can go file, import, load, you've got already a package that can start doing data analysis for you. You may not even know what you're quite doing, but you know what? You'll learn very quickly. You can start looking at different things, start analyzing your data in very efficient ways, and this certainly beats writing your own wavelet expansion basis, right? You can take all this, analyze things, pull out the kind of things you do. This is all time frequency analysis, essentially, what we showed today. Images are the time frequency analysis, the signals time frequency analysis, but all done with fairly sophisticated techniques, all which are very easy for you to get a hold of. Okay? Now, how are we going to use this in this class? The homework will go up pretty soon. Sorry, it's not up yet, but it will be very soon. I'm going to have you write your own Gabor, do a little bit of wavelet stuff too. I'm hesitant to require this for anybody because there's a lot of people who won't have access to it, so I don't want to make a homework. You use the Wavelet toolbox to do this, so we'll avoid that. But later, I will use it in some class lectures where one of the things that we're going to do is going to decompose cats and dogs into principal components and images and do statistical decision making. So this is coming down the road after we do all the image analysis lectures next week. What we're going to do after that is we're going to move on to linear algebra and the concept of linear algebra and how you can use it for this kind of stuff. And then we're going to tie it all together. Statistics, statistical decision making, time frequency analysis, and the linear algebra techniques. And we will do some wavelet analysis, but we'll only use it sort of as in a classroom lecture, and you'll see how it's being used. But basically, it's being used in this way, which is you take an image, calculate out what are the key things happening on different levels. And for instance, if you look at a dog, there are key things happening at different levels. If you understand that concept, that there's certain spatial structures that are happening for dogs that are different than cats, you can actually start thinking about recognizing images and so forth.